Okay, can I have everybody's attention? I want to welcome everybody to our first physics seminar after spring break. Today we've got Tim Giblin here, who's an adjunct professor here at UH Clear Lake. He's also a flight instructor at JSC. And before that, you were at
University of UNC,
yes.
Asheville, and
Yes.
College of Charleston for 7 years.
Yeah. So he is one of our adjunct faculty. He's also available for people who want to do research, independent study research. He's got one student working on a master's thesis right now. And with that, I'll turn over to Tim Giblin, and then if there's any questions, just feel free to ask.
Thank you very much. I appreciate the invitation to come and speak at your talking series this semester. The title of my talk is Gamma Ray Burst Shock and Relativistic Jet. The talk is structured kind of like a history. It's a very intriguing topic. It has a lot of history behind it, and we really have taken a journey over the last 4 decades or so since their discovery in the 1960s. And so what I'll do is I'll walk through that history and kind of develop the topic and kind of reveal how these things were actually come to become understood to a certain level. There's so much we don't know about them. And that's mainly because of their difficulty in detecting them and completing a whole series of observations that gives us a complete picture of their nature. So, and David, how can I advance? Okay. Okay, so gamma ray bursts were discovered. Actually, the announcement of their discovery was made in 1973 at a AAS meeting, but their discovery really came in the mid-1960s. The DoD, Department of Defense, put up a network of satellites called the Vela satellites. And these satellites were designed with gamma ray detector simulators to basically monitor the near-Earth environment for nuclear testing. Okay, so nuclear testing in 1963 was put into place for the U.S. and the Soviet Union in the height of the Cold War. We're not supposed to be doing any type of nuclear testing. Okay? So, what did they see? Well, they didn't find any gamma ray emissions from the near-Earth environment. So what they did find is that they found signals coming from just directly opposite to the Earth. Okay? So they called them cosmic gamma ray bursts. They're actually kept quiet for a number of years. Like I said, they were announced in 1973 at the meeting of the American Astronomical Society. Now, the difficulty in detecting these is you get basically a signal in one scintillator detector on one of the satellites. And you need multiple satellites to triangulate a location on the sky. And that was the big challenge then, because it took them a while to get the data. By the time they got the data, did the computation, the triangulation, figured out the location on the sky, it was 2 weeks later after the gamma ray signal was detected. Not only that, the location uncertainty of the gamma ray burst on the sky is typically on the order of about 5 to 10 degrees. So, yeah, so what do you need to put your telescope on the sky if there's 10 degrees in the view and scratch your head and say, gosh, what on earth? Can't say what on earth, right? What in the universe could have caused it? Well, any one of these hundreds of sources in the field of view, how do you know which one produced the gamma ray signal? Well, you don't. It's the bottom line is you don't. The question is, how do you do that? Well, you need to get a Swift detector that can give you an accurate location in a very timely manner. And that's been the biggest challenge that astronomers are posed with since 1973. And it literally took them nearly 20 years to get spacecraft in orbit where they could detect a lot of these things, get some good statistics on them, and try and understand the physical nature of these things. Now, the panel that you see here is just called the Lightcurves. This is basically a time history, so the y-axis is the intensity, the scintillator signal, which is just counts per second. And of course, the x-axis is time. And you can see there's a bright leaf here, and then it dips back down to the background, and then you see it. It's a little brighter, and then it kind of stays back to the background again. So, the Vela satellites last about 50 or 60 of these detections. And that was what we had to start with. Now, even after this time, interplanetary spacecraft were equipped with similar piggybacks. So we put a gamma ray spectrometer on an interstellar or intersolar system probe, and they would detect these things. But even then, determining the location was really difficult to get one detector. So you need multiple detectors to do the triangulation. By the time you did that, you still had poor location accuracy, and we had no idea what source of the star would actually produce it. So they were faced with a big challenge. There was a big push to put a dedicated high-energy gamma ray instrument in space that could do the job. So the outstanding questions initially were basically, what are these things? What are the burst progenitors? What type of cosmic objects would produce these gamma rays? And of course, what are the distance to the burst sources? Because that's going to put a beta constraint on the energetics of the source. All right? If it's very far away, then it must be very energetic in order to see the gamma ray too. Right? If it's closer, then you relax the energy requirements. So that was the key question to start out with. So NASA had this great observatory program. You might have heard of it. The Hubble Space Telescope is one of them. That's sort of the, the Queen Mary of the observatories. But there were others. The Gamma Ray Observatory was the sister of the Hubble Space Telescope. And it was solely dedicated to studying the high energy spectrum in space. Okay, so Gamma Ray was equipped with 4 instruments. It was equipped with an experiment called the Burst and Transient Source Experiment. And this was an all-sky monitor, scintillator detector, designed to operate in the 25 keV to the 2 MeV gamma ray range. So basically, hard X-ray to low energy gamma ray regime. And it would monitor the sky for these gamma ray bursts. And the detectors, here's a schematic of one right here, were placed at each corner of the spacecraft. So you had 4 on top and you had 4 on the bottom. And in that sense, there's the geometry of an octahedron, so you could get pretty much full sky coverage, excluding Earth blockage, of course. Okay. So when we get a gamma ray burst that would go off in the sky, and by the way, they were completely random in time and in location in the sky. We didn't know when the next one was going to go off, and we didn't know where it was going to go off either. So that was the need for an all-sky instrument like that. Okay, so by seeing a gamma ray burst and measuring its intensity in more than 2 detectors, so 3 detectors, we could triangulate, get a location on the sky. And improved our location. We improved our location measurements with BATSE, the burst transient source experiment, but it still wasn't good enough. Okay. Wasn't good enough. But our bulk of information, our bulk of knowledge came from this observatory, which was in orbit for 9 years. It was launched in 1991 by Shuttle Giblin and was deorbited in 2000 over the Pacific Ocean. There, in fact, was nothing wrong with the spacecraft. I worked on this mission from 1995 to 2000. All the instruments were performing nominal. It just kind of had ran its course. NASA headquarters tried to fight launch team on it, but they said, no, we're going to deorbit at the end of its lifetime. So it's touted as one of NASA's most successful scientific missions. We amassed information on 2,700 gamma ray bursts. Now, we would look at the data every single day from the spacecraft, and we would get, on average, about 1 gamma ray burst detection per day. And this panel here shows you a variety of the gamma ray light curves that we observed from BATSE. Now, we had a phrase that we would say, every day we look at this, and we would basically say, what could cause this? That's scratching our head. It became a running joke because they all look different. Okay? They all look different. If you look at any one of these and compare it with another one, you might see similarities, but they all look different. Okay? Some of them have a lot of structure. Some of them have maybe a single pulse type of a geometry. Some of them appear to have some kind of smooth geometry like this. None of them are spiky. Okay? So it's pretty obvious that they actually have a pulse type structure, from a bursting nature, repetitive nature. And that's not well understood. And so But you've got a pretty good database of GRBs that you can work with to try and understand that. Now, we can measure the duration of these events and find out how long do they last. Well, this is the duration distribution from the BATSE 4B catalog of GRB. And this doesn't include all 2,700. It's probably about 17% of GRB. And this duration distribution is bimodal. There appears to be a short group and there appears to be a long group. The short group is centered on duration slightly less than 1 second, and the long group closer to 100 or so. Now, this is a hint that there may be 2 different types of gamma ray bursts, short bursts and long bursts. So this led to classification studies. And to classify any types of scientific observations, it's good to get as many parameters or attributes as possible. So we look at the spectral domain next. See, what does the spectrum of a gamma ray burst look like? Because all the photons that we capture in the BATSE instrument are not all the same energy. They have a distribution of energies, right? So that's the spectrum. So the panel on the right, it shows a typical gamma ray burst spectrum. And that spans the energy range of about 1 keV up to several MeV. This burst here, this was GRB 990123, and we actually had some higher energy MeV observations from the EGRET experiment, which was one of the 4 experiments on the constant gamma ray observatory. So the top panel is the spectral flux. So it's basically photons per second per square centimeter per keV, and the one at the bottom is the energy flux. And it's essentially ubiquitous for all GRB spectra that they show broken power law, a smoothly broken power law. So there's a low energy power law and a high energy power law. Okay. Now the panel on the left shows basically a four panel time history shown in different energy channels, energy ranges. And that just kind of gives us some idea of the pulse structure. How does the pulse structure behave with time? And there seems to be a broadening at lower energies and a narrowness at higher energies. So the pulses tend to be narrower at higher energies, maybe around several hundred keV, and broader at the lower energies. This is the common property among all GRBs. You see this in 99% of all the events. Now, let me say one note about the spectrum here on the right. This is what we call a time-integrated spectrum, because after all, what we could do is we could take a slice here. We could take a slice in time of the gamma ray burst and ask ourselves, what does the spectrum of gamma ray photon emission look like? Okay? And we could do that all throughout the burst and ask ourselves, how does the spectrum change? Okay? And we do see a change. We see a spectral evolution. The spectrum evolves throughout the burst. On average, it evolves from a hard to a soft state. By hard, we mean high energy gamma ray photons compared to low energy gamma ray photons. Soft means the softer end of the lower energy gamma ray photons, maybe around 20 keV or so. So we basically make 2 measurements of a GRB in the spectral domain, time integrated spectrum and a time-dependent spectral evolution. That's a little more difficult because you need good statistics to be able to do it. And if you don't have good statistics, fitting this with a curve, with a smoothly broken power law, becomes much more challenging. And that has been a very challenging modeling problem. I won't say a problem, but it's been a challenge for us to be able to do that and accurately determine what the spectral indices are here. For example, what's the power loss slope here, what's the power loss slope here, and what is the peak energy. You define the energy where the spectrum peaks at E peak, okay? It's basically where's the bulk of the energy of the gamma ray burst in the spectrum. Now, one interesting point of this, and this is probably the most important point, is that it is a non-thermal spectrum. Okay? Pretty hard to make thermal gamma rays. So whatever is producing this event must be some type of particle acceleration, some type of electron acceleration process that's responsible for that. So the theoreticians immediately took that and went, okay, what kind of models can we construct that would produce this type of emission? Immediately, things like supernovae come to mind, shock waves, very high energy processes, shock outflows that could produce that type of energy. So we'll come back to that in a little bit. So by doing all the spectral modeling of these GRBs, we can look at the distribution of E peak, okay? So where that spectrum peaks. And it's typically around 250 keV. Yeah, it's a pretty narrow distribution. And this is hinting at there's probably some type of commonality here. So maybe some common denominator among all of these things. Maybe a single process, or very similar process, is responsible for producing all of these gamma ray bursts. So we've got temporal information, we have spectral information for the gamma ray bursts. So these are two important attributes that we use to initially start to classify gamma ray bursts. We have long gamma ray bursts, we have short gamma ray bursts. This is a plot of hardness ratio versus P90. P90 is our measurement of duration. So the hardness ratio is basically telling us relative number of hard photons versus soft photons. So the higher the hardness ratio, the more energetic photons are found in the spectrum. And what does this look like to you?
Bimodal.
Yeah, probably two populations there that overlap, okay? You might look at it and say, well, that's a shame. I wish we could have two populations that were nicely separated. So there's a gray area there, right? Darn. That's going to make things more complicated. As if things weren't complicated already. But that's the general trend here, is that you have a short class that appears to be spectrally harder. In other words, on average, they release more high energy gamma ray photons than the long gamma ray bursts, which would populate this class here. And just by looking at this, you can tell which group or which class tends to be more populous. The long. So there are more long GRBs than short GRBs. So the cutoff there between those classes is about 2 seconds. Now, what about the sky distribution? Okay, BATSE can calculate locations for all these GRBs, but again, the accuracy was not that good. The best we could do was maybe about a fraction of a degree at best. Okay, and therefore, the brightest burst in our sample were the ones that accurate we could locate with the best accuracy. This is a sky distribution of 2,704 events detected by BATSE. Now, this is in galactic coordinates, okay? So, one of the things that astronomers are going to do, since the location is so poorly known, you couldn't pinpoint them to a specific star in the sky, is, well, what does the sky distribution look like? Because we don't know how far away they are. So therefore, we don't know the energy output of them. So this is the obvious thing to do. Let's just make a galactic plot so we can see the disk, see all the gamma ray bursts from the disk of our galaxy, right? Wrong. That's not really wrong. We see an isotropic distribution here. And there's been all kinds of error analysis to say, well, it's really a galactic disk and the location here doesn't work. That argument doesn't work. There are a lot of people that tried to prove this, and the errors are contributed to the isotropy here, but it didn't work. So the brightest stars in the Milky Way follow a band like that. Milky Way and infrared in the disk of our galaxy. And of course, we have the distribution. So what does that mean? Well, it means that galactic neutron star models for GRBs are ruled out by this alone. Now, why would the astronomers propose a galactic neutron star as the source of the gamma ray burst? Well, what produces a neutron star? Collapse of a massive star, right? A supernova will leave behind a neutron star or a black hole. And it was known at that time that neutron stars in binary systems to accrete matter from their companion star, from the donor star. And in the process, the gas rolls around, hits the surface of the neutron star, heats up, produces an explosion, and you get an X-ray burst. This was observed by, there are several balloon experiments actually done in the late 1960s, flying X-ray detectors at high altitudes that observed these X-ray bursts. And they were known, but the geometry here, the distribution doesn't afford a galactic neutron star model. It just doesn't work. So a neutron star in a binary system would produce something like this when it accretes enough matter onto its surface, and you see a rise in X-ray flux and a pretty smooth decay. It lasted several tens of seconds. So we knew that process fairly well. In fact, this was a big observation that proved that these neutron stars were actually in binary systems. These were called X-ray bursts, and they were known at the time. Okay? So people likely just made the connection, well, maybe a gamma ray burst is just a zooped up X-ray burst. But the isotropy of the distribution didn't show that. Okay, so the next challenge for us is to try and detect gamma ray bursts in another part of the spectrum other than gamma rays. Do they emit in optical? Do they emit in X-rays? Do they emit in the radio part of the spectrum? Well, it turns out they emit photons all over the electromagnetic spectrum, as we know now. But at the time, we didn't know that. So an Italian-Dutch satellite called BATSE was put into orbit in 1996. And it was equipped with a sensitive X-ray detector, which actually had imaging capabilities. And they basically monitored the sky in the 40 to 700 keV range, perfect for gamma ray bursts. E-peak fits right into that detection window. So they detected a number of GRBs when the satellite was in service, and they could localize using the X-ray detectors with arc-minute accuracy. That's something that we can use to get a telescope on and pinpoint sources in the field of view that could produce something like this. We didn't know what we were going to find. Okay. So what did we find? We found this X-ray afterglow. So it's a persistent X-ray emission that follows the gamma ray burst at later times. Okay. So the gamma ray burst goes off, and the X-ray afterglow is observed at later times. And these light curves, or the images here, actually shows you that the X-ray afterglow, which is the central point right here, actually fades with time. And it fades according to a power law. And this is GRB 970228. By the way, the GRB naming convention is 5 days. So this is February 28, 1997. And the BATSE instrument detected a number of GRBs, and detecting the X-ray afterglow turned out to also be a common denominator among GRBs. Most GRBs have this X-ray afterglow. And the light curves that you see at the bottom here show observations at late times. Now, this is a logarithmic plot here. So we're at 10 seconds, 100 seconds, 1,000 seconds. So the initial trigger of the burst is here. And you can see out to here, you're at 1,000 seconds. These are actually upper limits here, but these are actual data points. The BATSE satellite was also equipped with narrow field instruments where the spacecraft could actually slew once it determined the location from its wide field X-ray camera. It could focus in and get our second imaging resolution. So these X-ray afterglows could be modeled with the power law we take this time. And this is some work from Luigi Piro et al. That came in the late 1990s, which show several GRB X-ray afterglows. The panel on the left is an interesting one, 970508. It shows the initial burst, which is up here, and it's observed in X-rays. So that's also telling us that we can see the prompt, what we call the prompt emission, which is the traditional gamma ray burst. We can also see that in X-rays as well. But at later times, it appears to obey this power law but there's actually some points that deviate from that power law, which suggests that, well, maybe something is still going on after this GRB has gone off. And look at the time scale here. This is, that 10 to the 5th? Right? Can't see it on the screen. Yeah, 10 to the 5th seconds since the burst went off. So there's definitely something going on there. 31 out of 36 X-ray afterglows were detected by Beppel Sachs. Now, I mentioned just a little while ago that we can see these now across the entire electromagnetic spectrum. So folks with ground-based telescopes said, okay, get us these locations as quickly as you can, somehow. And that way we can train our optical telescopes on them. Because as long as we have arcing and accuracy on a location, we should be able to identify some optical source there, if there is an optical source there. So the hunt was on at this point. A rapid response gamma ray burst coordinate network was set up to disseminate the spacecraft locations to the ground to optical observers. And actually now it's completely automated with the Swift spacecraft, which we'll get to in a few minutes. That whole process is automated. And you can literally get a gamma ray burst location on your cell phone in about 10 seconds after one is detected by the spacecraft. So yeah, it's pretty amazing how far we've come. So 970228 was the first optical detection of a gamma ray burst. And this was 21 hours later with the William Herschel telescope, 4.2 meter telescope. This was actually done by some graduate students, friends of mine. Actually, my advisor is Jan van Paradise. He was a Dutch astronomer who since passed away, but he had graduate students in the United States. He had graduate students in Holland. And those guys were the optical guys, and I was looking on the high energy stuff. And so Jan had them, they were at the telescope, got word of this GRB that went off. He had them train the telescope on there, and boom, they found the optical counterpart. And notice that it's right here, and it's faded, okay, after a number of days. So it's basically gone. So it's slipped into a fading decay phase. Now, follow-up observations were made with Hubble Space Telescope that revealed an underlying host galaxy. You can see the point source right there, and the host galaxy colors right there. And from that, spectral observations of O2 and O3 lines produced a redshift of about 0.7. Okay? Now, this is the holy grail that they're looking for to establish the distance scale. The isotropic distribution suggested that the distance scale was a cosmological one, GRBs, and not galactic. But it wasn't definitive proof. We needed the direct observation to demonstrate that these things indeed were cosmological. So if you pick your favorite cosmological model, calculate the luminosity distance as a function of redshift, which is about the Hubble parameter, and you get the distance on the order of gigaparsec. Okay, that's way the hell away, right? So these things were in fact cosmological, or at least this one was, right? So this is one burst, right? So the hunt continues for more bursts. And we found more bursts. Beppel Sachs, the several dozen bursts that Beppel Sachs identified with X-ray afterglows, optical afterglows were then found, and additional, more detailed observations were made. Now, what do those optical afterglows look like? Well, this shows two panels. Again, optical flux versus time, just a time history. It shows also kind of a power law, but with a break in it. So it's a smoothly broken power law. And it appears that this happens in several different optical colors. And that's why you see three different curves here. The VR and I filters, if any of you are familiar with optical astronomy. So the Lightcurves exhibit a break. A break wasn't seen in all of them, but the majority of them showed this break at late times. And that's typically several days, although some of the breaks have been found at very early times. There have been a few that have had breaks with less than 100 seconds after the GRB took place. So there was a big effort to put together what we call rapid response automated systems on the ground. Optical telescopes that, if given the information electronically, automatically could just respond to the location of the sky, get to the location of the sky, start taking the images. And this was a big challenge because these things are faint. The magnitudes, I didn't point it out, but at late times after the burst, the magnitudes are down to like 15, 16, 17, 18th magnitude, okay? Even just 10 hours after the burst. So, and also keep in mind, you don't know when, you don't know where the next burst is going to occur. So really what you need is a network of optical telescopes that sweep as many latitudes as possible across the Earth, okay, to get the coverage that you need. And you don't want big telescopes either, because you want something that can sleuth fast. So a lot of small observatories were designed. There were some neat proposals that came out to achieve this. One of them, which has been the most successful, is ROTSE, the Rapid Optical Transient Source Experiment. And they have sites in Australia, Namibia, Turkey, as well as Texas. And it's basically a half-meter Cassegrain telescope that can automatically respond to triggers from spacecraft. And it does it all automatically. Now, ROTSE made a huge discovery from GRB 990123. Okay, these panels show the light curve of the gamma ray flux, as the prompt gamma ray burst emission. This telescope was able to get on the burst while it was still going off. The burst was still bursting. Yeah, we've had, I think, at least a dozen of these now since this happened in 1999. They've been able to get on the burst quick enough. Now, obviously, this is more advantageous if the burst is long. For short bursts, it's almost impossible. So this one had the optical flux that peaked, looks like it peaked right here. Now, what you run into there is running into the problem of not having enough data points to sample the entire light curve. Right? So you only have a few optical data points. Now, whether or not it really peaked at this point, the three observations that they had here that were coincident with the prompt emission seem to suggest so. And the bottom panel shows, again, this broken power law decay. You can observation points here, models of the power law, and then a bunch of observations that came in later with this power law. So again, the broken power law seems to fit. I just thought I'd throw this in to show you some of the areas that across the globe that are establishing robotic telescope systems. This one here is one that I put together with some colleagues from now in the St. Thomas. It's a half-meter automated telescope, and it automatically responds to GRB triggers. We've had some personnel issues down there, so we're currently down. This is the facility right here. Okay, let's take the observations to talk about the energetics of gamma ray bursts. And this gets into really deciphering the physics of these things. What kind of physics can we extract from the observations? Well, we can define some things, a peak flux and a fluid parameter. The peak flux of the burst is just the maximum flux of the burst that's observed. So it would be the peak. You see multiple pulses in a gamma ray burst, some are brighter than others. You pick the peak. And there are some issues with that, defining the peak flux on a certain time scale, but typically 256 milliseconds is the time scale that we choose to define a peak flux. The fluence is just a time-integrated flux of the burst. So we integrate the flux over the duration of the burst, and that gives us what's called the fluence. So that should be some direct measure of what parameter in terms of physics. That one, right? To measure the energy output of the burst. Right? So we need to know what the distance is, though, right, in order to determine what that energy output is. So for cosmological GRBs, the right expression for E gamma, which is the gamma ray energy output, and I put an iso subscript there, meaning isotropic. Isotropic meaning that whatever the source is that's emitting the gamma rays is emitting isotropically, uniformly in all directions, in other words. And that's a big assumption at this point because that's all we have to go on. But it's the simplest, right? So E gamma iso, 4 pi d squared, dl is the luminosity distance, f is the gamma ray flux. And of course the 1 plus v factor in the denominator. So with these numbers, we can calculate these things. Let's see if we can, before we get into that, let's see if we can understand some more about the source that's producing this type of emission. We know the source must be compact, and we know that because we look at the variability time scale of the gamma ray burst time history. We see very short fluctuations on the order of milliseconds. So if we just consider a simple cartoon here, say we have a spherical source like this, whose radius is r, and you have some observer over here at some distance. Then r is roughly equal to c, where c is the speed of light times delta t, and delta t is just the duration that you observe. And for those short durations, we see that our source size r must be fairly small, right, on the order of 100 to 1,000 kilometers in size. And that's, again, extracted from just one observation of the size of the pulses that we see in the gamma ray burst. Okay, now here's where things get really interesting. This idea was put forth by Martin Rees, originally back in the 1970s, that whatever the source is, it must be expanding at relativistic velocities. Now, why is that? It's related to an opacity issue, or something called the compactness problem, where we just demonstrated that the source must be compact. But if you have that much energy in that small of a volume, you run into this pair production, gamma-gamma pair production, producing electron-positron pairs. Okay? So we know what the optical depth is for that, and we can write that expression here in terms of the luminosity, the size of the source. Sigma t is the Thompson electron scattering cross section. And from that, for a given distance, we can take some distance measures, d of 100 parsecs, 100 kiloparsecs, 100 megaparsecs. And from flux measurements, we can put those into this equation and calculate what the opacity, pair production opacity would be. And for our galactic distance scale, we can get an opacity of 1 if we assume a distance of 100 parsecs, and that's good. That means we can get the radiation out. Okay. In other words, the source can be optically thin, the photons can escape. But at much larger distances, the pair production opacity is high. It's ridiculously high. And in fact, a lot of astronomers use this argument to say that GRBs are not cosmological. But Martin Rees said, well, wait a minute. If we allow the source to expand relativistically, we can circumvent this problem. So he introduced a Lorentz factor, which you guys know from your modern physics, 1 over 1 minus square root of 1 minus beta squared, and perform some magic. You can calculate the new expression for the pair production opacity, and it goes as d squared times f, f is the fluence of the burst, over gamma to the 4th power, the Lorentz factor. If you solve this for gamma, you get value and demand that the opacity is 1, so that the source becomes optically thin. You get values of the Lorentz factor of 100 to even 1,000. So it's by imposing these arguments, they're able to deduce that, wow, these things are cosmological distances. They must be expanding relativistically, so some seriously energetic source must be at work here. And so they came up with this idea called a relativistic fireball, where you have some compact source that releases an enormous amount of energy, expands relativistically, and somehow produces a gamma ray burst. Well, it was first thought that this emission was spherical, so that it would go in all directions, right? But then they started thinking a little more cleverly. This was a guy by the name of James Rhodes in 1999 said, well, maybe these things are actually jetted or beamed. Okay, so that means that they have a conical type of structure. Okay, maybe like a bipolar jet or something like that. And those are not unheard of in astronomy. Right? We know about these in protostars. We know about them in X-ray binary systems, black hole binary systems, AGN, quasars. So maybe a gamma ray burst has a similar type of behavior. So if this thing is expanding relativistically, then there's a relativistic beaming effect where the radiation that you observe from that source is beamed into an angle, a half-opening angle of 1 over gamma, where gamma is the Lorentz factor of the ejecta of the flow. So theta B would be the beaming angle, and here's the observer over here. So your radiation will be beamed in that cone. If the flow is collimated, defined by some jet opening angle, theta J, okay, then you would still observe this, right? But at some point, if this thing is decelerated, if it's slowing down, then this beaming angle will surpass the jet opening angle, and you will actually observe less radiation. You'll see a break in the light curve. So that's kind of like a clue saying, oh, it's not spherical emission, it's actually jetted emission. And so the break that we see in the light curves, in the optical light curves, and it should be an achromatic break. This is actually a hydrodynamic effect. And this jet break that we see, or the break that we see in the light curve, could be explaining the jet geometry of the outflow. So, if indeed these things are jetted, which it appears they are by their afterglows, then that relaxes the energy requirements a little bit. And that's okay for us, because we're talking about an enormous amount of energy. If you calculate the isotropic energy, you get values around 10 to the 54, 10 to the 53rd ergs, okay? And if we take the beaming fraction into account, FB, okay, then we relax the energy requirements substantially, and we get energies around 10 to the 51, or still an enormous amount of energy, still more than that on the supernova. So it appears that these jetted relativistic events here are packing more energy than a supernova, and they're doing it in a shorter amount of time as well. This plot shows just some statistics on the energy distribution. This is it's a little outdated, it's not the most recent one, but you can see that it peaks right around between 10 to 50 and 10 to 51. We call them faux 51 erg. So if you hear the term faux, that's its origin. So how do we produce a gamma ray burst from a relativistic outflow from a very compact source? Well, somehow the kinetic energy in this relativistic outflow must be liberated. And there are a number of researchers that looked at this. Again, a lot of this was spearheaded by Martin Reich and Peter Meseros at Penn State University. And they came up with shock models that, well, this flow is probably unsteady. It's probably not a steady flow, it's an unsteady flow. And in an unsteady flow, you build up internal shocks. And that's one way you could liberate the kinetic energy. Okay? So they came up with basically two scenarios, an internal shock scenario and an external shock scenario. And in the internal shock scenario, you liberate kinetic energy to flow into radiation by shocks that are actually within the relativistic ejecta. The external shocks, when the relativistic ejecta encounters the ambient medium surrounding the source. So for example, if it's a star, a massive star like that, a supernova together, then that star is embedded in some type of a cloud, typically. Okay? At least we can say that there's interstellar medium surrounding the star. And depending on the environment, if it's in a molecular cloud or if it's not, the density of that environment will change. But that outflow will at some point hit the external medium and begin to sweep up matter. Right? And when it sweeps up enough matter that's comparable to basically E over C squared, which would be the total energy in the outflow divided by C squared, When it sweeps up a mass comparable to that amount, significant deceleration sets in. And that's called the external shock. So that deceleration will also liberate kinetic energy in the form of radiation. Now, based on our discussion so far of the observations of prompt gamma ray burst emission and afterglow emission, which one of these do you think would be responsible for, say, the prompt gamma ray burst emission? Internal shocks or external shocks? Probably internal shocks, right? The external shocks are attributed to producing the afterglow. And the afterglow is this long, extended emission that happens, hours to days to weeks, and even months in some cases. So we devised some simple models about internal shock, where you just consider the relativistic outflow as shells. And these shells, each one of these shells has a Lorentz factor, which basically defines its speed and defines its kinetic energy, right? And if you have a distribution of those Lorentz factors, then you're going to get shells that collide with one another. And you're going to set up shock fronts at each one of those collisions. And those collisions are responsible for producing the gamma ray burst pulses. So, got a cartoon here that kind of lays that out. We have an inner engine, and we might comment on what that inner engine might be in a little bit. And we have an ultra-relativistic jet and a conical type geometry. Okay? And these fronts here, just want to give you a graphical representation. And it's a very crude way, because really it's probably turbulent. The process is turbulent inside the flow, so it's not going to be, we used to call them flying pancakes, running into each other. It's not going to be that simple. And I'll show you why. I have an MHD simulation to show you in a little bit. So at some point, depending on the distribution of matter in the medium surrounding the source, this relativistic outflow will be decelerated by the ambient medium. And at that point, you produce a forward shock, but you also produce a reverse shock. And in the co-moving frame of the ejecta, basically have velocity going off in both directions. Okay, at that shock front. Let's see, got about 12 minutes or so. So I want to talk a little bit about the radiation mechanism. Okay. Our model, internal external shock, must be able to produce the observed spectrum that we see. And the most likely candidate in the process of actually producing the radiation, in other words, how do we get the gamma ray photons, is synchrotron emission. So basically, relativistic electrons in the presence of magnetic field, and magnetic fields themselves can be produced by the turbulence inside the flow. And we get a synchrotron spectrum, which is a complex spectrum. I won't go through the entire thing, but it has a break in it. There's two breaks in here. There's one here and one here. So we have a slope here, here, and here. And these breaks are determined by the time scale at which the electrons can actually cool compared to the hydrodynamic time scale of the shock. So there are two different scenarios that we can get here for electron cooling, radiative cooling of electrons by synchrotron emission. And we compare that with our observations. Do our spectral slopes match that of synchrotron emission? The bottom line answer to that is they're pretty good for the afterglow emission, not so good for the prompt emission. We have a really hard time reconciling all the prompt GRB spectra with synchrotron emission. So there must be some other process at work there. Some of the processes that folks are considering are inverse Compton. So you have basically a hot population of electrons, and you have photons that are upscattered off of those electrons, which would change the spectral slope of the prompt gamma ray emission. So there's been some success with that. I wanted to show you this burst because this was kind of a seminal event, GRB 980923, that was observed by BATSE back in 1998. And one thing that we don't know, and this is because of our observations are so limited, is the gap between the prompt emission and when the afterglow starts, because there's this delay time of when our X-ray detectors can get on the burst versus when it's detected in the prompt gamma ray emission. So there's kind of this fuzzy region that's unknown about when the prompt emission actually ends and when the afterglow starts. And does the afterglow start during the burst? Does it start after the burst? Is there a time delay between the two? If so, is that telling us something about when an external shock begins, or does an external shock begin during the gamma ray burst itself? This was a burst that was observed by BATSE on GRO, and it showed this very smooth tail, very long tail here, that could be very easily modeled with a power law. So this burst was extremely bright. It was in the top 5, actually, in peak flux among the 2,700 BATSE GRBs. It was very bright, had a lot of pulse structure here, and then the pulse structure just stopped, and it was just a smooth power law decay, indicating that maybe this is the actual afterglow, and we're seeing the afterglow starting during the actual gamma ray burst itself. This is a log plot here, so it looks different than this one, but this is the prompt emission, and this is the smooth power law tail. So we started looking at some additional events that showed a gap. Gamma ray bursts that showed a quiet time. So we call them quiescent gamma ray bursts. Gamma ray bursts that would turn on, pulse for a while, then they would be quiet, and then we'd see some emission again. And we're looking at the properties of that emission compared to this prompt emission. So you can see the secondary emission here, or sometimes we call it post-quiescent emission. And so we're trying to make that connection between afterglow and prompt emission. So there are two possibilities here. This could be still due to the progenitor, and this could be due to an external shock, if we adopt the internal external shock model. So these two bursts here particularly do not show consistencies with prompt emission. At least the post-quiescent emission here doesn't show a strong consistency with prompt emission. So our conclusions there are that there must be another process at work, perhaps that is the external shock. The luxury that we didn't have with the BATSE burst is having the X-ray afterglow. That came after BATSE. So I'm going to go ahead and skip that for the sake of time. Now, the NASA Swift spacecraft was put together with the idea in mind to get rapid locations to the ground as quickly as possible so that we could get early optical observations from the ground. So Swift was launched in 2004, complete GRB dedicated observatory spacecraft, equipped with 3 main instruments: the Burst Alert Telescope that observed in low energy gamma rays, an X-ray telescope, and an ultraviolet optical telescope. The UVAT and the XRT are actually collimated. They're co-aligned, I should say. And this one here is the Burst Alert Telescope, which is planar, so you can basically see 2 pi squared radians. And so this guy sees the gamma ray burst, computes an onboard location in a matter of 2 to 3 seconds. And then the spacecraft flight software makes a decision, do I want to look at this gamma ray burst? Most of the time it's yes. And so the spacecraft will autonomously slew and point the XRT and the UVAT instruments to get the X-ray afterglow and the optical afterglow. This is an example of one GRB, one very bright GRB that was detected by the Burst Alert Telescope on Swift. And I'm just going to swiftly move through some of these since we're short on time. This is a ROTSE-III optical counterpart detection that was made 26 seconds after the burst. So basically Swift disseminates that location to the ground. Like I said earlier, you can get it on your cell phone if you want. You can sign up to get these. Or you could have a socket connection right to a ground-based optical telescope and get that position sent, again, in a matter of 5-6 seconds. And depending on how fast your optical telescopes can slew, you can identify, in fact, if there is an optical source there or not. This one was at 13.6 magnitude. Very bright. Now, Swift has measured a bunch of X-ray afterglow. Swift has measured about 650 bursts per day. And it appears that the X-ray afterglow of these events has some type of a canonical behavior. That is, basic general trend. And it shows up as basically three power law segments in the X-ray afterglow. One with power law index alpha 1, alpha 2, and alpha 3. So apparently there's a very steep decay initially, and then it shallows out here, and then you see even steeper decay at later times. The current interpretation in terms of the internal and external shock model is that the external shock is this emission right here, and that this guy right here is still the gamma ray burst prompt emission, but you're seeing called the curvature effect. If you're seeing the source expand like that, you're basically seeing high latitude emission. In other words, if it's conical, but if it's conical like that, and you're looking along the line of sight of the jet, you're going to see that high latitude emission from the jet radiated front at a later time. And so you're going to see a steep decay here. But as the external shock sets in, at some point that emission is going to dominate over the fading prompt emission like that. That's the current interpretation. There are some details about this that are not quite clear. There have been some papers that have looked at how the spectrum evolved during that day, and there's some real inconsistencies there. So we need more data on that to understand it. The second break here is interpreted to be this jet break that I was explaining to you earlier. Right. So at that point, the matter is basically swept up by the interstellar medium, or the jet has been decelerated by the external medium at that point. So one of the things that we're looking at, and Tom is doing some of this work for his thesis, is he's looking at these quiescent episodes and trying to define common behaviors and seeing what we can learn from that. And this is the GRB 060526, which is observed by Swift. The plot on the right here shows the gamma ray emission from the Robotic Telescope, as well as that from the XRT, the X-ray observations that came shortly after the spacecraft flew. And the panel on the left shows the traditional linear gamma ray time history, and in fact, is one of these quiescent bursts of the pulse here. But look at this. Here's the X-ray afterglow, and there's this big flare in the X-rays. And Swift is seeing this X-ray flaring in about 50% of its GRBs. Not all of them do the flare. So, question, is this part of the deceleration of the outflow? Is the external medium producing this flaring? Or perhaps the progenitor, whatever produced this relativistic outflow, is still active? And that's something that theorists are puzzled with right now because it's quite a long time. We need a time scale here. You're at several hundred seconds after the burst went off. So whatever is producing this flaring, if it is the progenitor that's responsible for this, it must be active for a long time. So let's take a few minutes and just ask the question, what is the progenitor? What produces the relativistic outflow? Well, supernovae are the likely candidates to take a look at least first. But the energetics here of the gamma ray burst scaled up slightly from GRBs. We know that supernovae are produced by the death of massive stars, and they have outflows, and they plow into the external medium, and we can model that. We know what their light curves look like. We know what different types of supernovae that are there. So we could try and use some of that modeling to try and fit it to gamma ray burst data, or at least see if there's some commonality between the two. So suppose that a collapsar model has been generated by supernova expert Stan Woosley and a lot of his collaborators, where you have a massive helium star. So basically, it's a very massive star that's lost its outer hydrogen envelope. Okay, and eventually its core is going to collapse. In the process of the core collapse, it produces a black hole, and it's rapidly rotating. And in that process, it produces bipolar jet. And the rest of the star doesn't even know what's going on at that point. So these bipolar jets basically drill their way through the stellar mantle and burst through the stellar photosphere and out the star and then plow into the ambient medium around the star. They've done a significant amount of magnetohydrodynamic simulations to demonstrate that. This is one of their simulations of a collapsar model. And the idea here is that the core of the star is on the left, and the relativistic jet has been produced, and you can see the turbulence on either side of the jet here. And so the blue there is basically the photosphere of the star. And so the jet eventually plows through that photosphere of the star, and it takes some of it with it. So there have also been some models proposed that, well, maybe there's a two-component jet model where you have this relativistic outflow, but you also have a cocoon around it initially. And that cocoon could be responsible for some of the features that we see in the afterglow Lightcurves. So, are these related to supernovae? Well, there have been some GRBs that have been temporally coincident with supernovae. And the spatial location has been the same too, and this is kind of interesting. Yeah, this is an event here. Can you see the galaxy here? Right? All GRBs have a faint host galaxy. It's another definitive observation that demonstrates that they're cosmological. They all have a host galaxy. The host galaxies tend to be dwarf, irregular type galaxies. This one is actually one of the spirals, very well-defined spiral. But you can see the identification of the source there. And the spectra. The spectra show a lot of what we see in supernova, and the basic shape match up nicely with that in supernova. Now, a lot of bursts we don't have the best observations for, but some of them do show the supernova, or what they show a bump in their light curve that could be interpreted as a supernova, a late-time supernova. So these are just several light curves that show this power law decay, or the optical afterglow of GRB. And then there are some additional points here that sort of hump in the light curve. So if you superimpose the supernova optical light curve and the power law, you can get some pretty good matchups here with the observations. Is that definitive proof? Definitely not definitive proof, but certainly suggestive that that's one interpretation. This plot is for GRB 050525A, which I think is a little better representation of what I just explained to you. So this here would be basically the DC level of the host galaxy. This would be the decay of the afterglow, optical afterglow, and of course the supernova hump that occurs at late times. Now, an alternative interpretation there, this is GRB 030329. The light curve in the middle, actually it's not a light curve, it's a spectrum. The spectrum in the middle is the noisiest one, but it shows a very similar shape to 1998 BW, which is the bottom one, and 1998 BW, which is the top one, also at different times. One is at the maximum, and then one is at 7 days later. Now, an alternative viewpoint was proposed by Jonathan Greneau and his collaborators that, well, it's probably not a supernova. We're calling them refreshed shocks. So again, it's the idea of a progenitor being long-lived and extended and still being active and producing emission at late times. Okay, so one last thing. For the short bursts, what about the short burst? Because the whole picture of internal external shocks really didn't work that nicely for a short burst because, well, they're just very short. And the current leading theory for that is a neutron star binary system. So it's a binary system of two neutron stars gravitationally bound to one another. And they will eventually coalesce, tidal forces will take over, rip them apart, and produce a GRB. So this is the current leading theory for that one, which probably could be dedicated to a whole nother talk. But yeah, it's an interesting theory. So just to summarize some basic concepts about gamma ray burst that I'd like you to take away. Source must be compact and expanding relativistically. In a jet-like structure, seems to be ubiquitous among GRB observations. Extremely luminous. You might hear this term hypernovae in some of the common literature in reference to gamma ray bursts. That's where that name originates. Hyper meaning relativistic and more energetic than supernovae. There appear to be two classes of GRBs, but additional observations like optical afterglows, post-galaxies, things like that are being added into the mix to refine our classification. And of course, we have an association with supernovae. Not all of them are associated with supernovae, but it's interesting that that a certain fraction, probably about 10%, I would say, right now, actually have associated supernovae observations. So, if you'd like to know everything about GRBs now. Yeah, it's a pretty fascinating field. I'm happy to entertain any questions.
For short course gravitational, short course gamma ray bursts, if that's a neutron star collision, and it would also be emitting gravitational waves. You know about what frequency range that would be?
I couldn't give you any numbers off the top of my head, but that's one thing that they're going to look for is gravitational waves with some of the upcoming experiments.
The thing is, somewhere 100,000 hertz or something.
Yeah, yeah, I would imagine it's high. Yeah.
So after the Space Telescope detects the gamma ray burst and the Earth-based ones optically look, how long when it's focusing on that spot? It looks like if it's a supernova, they're going to be like a week or 2 weeks later.
Well, it could be. They're focusing on as much as they can, whatever kind of window of observation they can get. And you got to remember, ground-based optical astronomy is governed by weather, the diurnal cycle. You know, and that's why it's important to have, you know, telescopes that have a wide range of latitudes. Because where one telescope is observing the burst, and then, oh, it's setting, but they can't see it anymore, right? So somebody else has got to pick it up. So that they're really constraining there. So we need really multiple observatories on the ground. This is what they do. The optical guys do. You know, they coordinate on the ground and say, okay, we have observations to fill in this time frame. You guys have observations to fill in this time frame. And of course, they have to calibrate their data, and it's a big task.
But if you were detecting one per day, there's no way you have the telescope resources to.
That's right.
Wow.
It's a big challenge, and that's been a big problem. But I mean, you saw the date 1997, like the first optical transient detection and optical afterglow. That's what 13, 14 years ago, and we still have a long way to go. But a lot of astronomers, optical astronomers, are putting together systems that, well, they can't do it all, but they can at least observe. One system down at CTIO, Chile has I think they have 4 identical telescopes, and they observe in different wavebands, BVRI, basically photometry, so they could get afterglow color information, which is really important. But again, they can't do it all either because of the limited sky coverage, where the burst happens to be on the sky. So, and we've done some analysis for our telescope in St. Thomas. You know, we can calculate, well, the burst goes off here or there, whatever position in the sky, how long is it going to be up? In fact, I had a student write some code that would basically give me a text message saying, as soon as the burst goes off, the position is known, so it would say, okay, it's going to set in 4 hours, you can get this many exposures in or whatever. You do like a observing scheme, and you put together a plan that way. It's not easy. Yeah.
Why is the twin solar mass, helium star, not making heavier elements?
It's a rough number. All it is making heavier elements is cool. It's called a helium star because the hydrogen shell has been blown off by massive stellar wind.
Wolf-Rayet star?
Yeah, like a Wolf-Rayet star, exactly. So the more massive stars, the more luminous ones are going to have stronger stellar winds, and they're going to lose their hydrogen shell. And the type 1C supernova is a huge shell. But they're definitely making heavy elements in the core. And another thing that's interesting to point out that I didn't comment on is that if these massive stars are responsible for the long classic GRB, and it looks like they are in some capacity, then you expect to find them in regions in the interstellar medium where you have dense clouds, you have star formation going on, because they're going to live their lives very rapidly, on the order of 10 to 60 years, right? And they're going to live in environments where the interstellar medium may be very opaque, unless their stellar wind is blowing out a bubble and a cavity around the star and whatnot. But depending on what is between our line of sight, what is along our line of sight and the star, there may be a cloud, there may be bursts going off that we can't see the optical afterglow. And that's an important point too, because we only see optical afterglow for about 70% of these events. We don't see it for all of the events. These are called dark bursts. So that's an interesting indication, because it's either telling you something about the environment of the progenitor, or it's telling you something about, your model's just wrong. So which way do you go? Well, you start amassing more data. That's been the history of GRB science for the last 40 years. It's been a long way. Yeah.
The base-based generator detectors is the reason why they don't have optical telescopes on them, just so the fixed and heavy, it's difficult to put the optical observation.
Yeah, I mean, Swift is the first one in this generation to really do that. But here's the problem: is you don't know where and when the gamma ray burst is going to go off. So your gamma ray detector has to be all sky mounted. Now, you use that term loosely, all sky. Well, you get as much of the sky coverage as you can, right? And yeah, but get an optical detector up there with it, right? But if your optical detector is looking, at that region of the sky, and the burst goes off over there, then the burst detector, it will be detected, right? If you're at some angle like this, but it won't be able to be the optical detector. So therein, the spacecraft has to swim. And Swift has onboard software. Flight software can make that determination, and they can, change parameters and whatnot. But it can fly pretty quickly in a matter of 10, 20, 30 seconds, depending on the location, of course. And there have been some detections. I think there's been about a dozen or so, maybe more, of where the burst just happens to be in the field of view of the optical detector and the X-ray detector and the BAT. Obviously, if it's going to be in the field of view of the optical and the X-ray detector, then it's going to be in the field of view of the gamma. Yeah.
A couple of questions. One, the estimate of distance from redshift, is that based on the host galaxy division or?
Great question. In some cases it is. In some cases, it depends if we get spectra of the afterglow, but a lot of times it comes from the host galaxy spectrum, which is more long-term.
It seems like it's from the effect itself, if it's a relativistic thing, that's going to change your computation of the distance on the redshift.
Yeah.
The other question is, in some cases, like we'll come up to X-ray flare, something where there's another pulse several hundred seconds later. Has anyone considered maybe a case of a reverse shock from the opposite direction?
Actually, well, there is a reverse shock that's set up. When you have in the external shock scenario, you have the forward shock and you have the reverse shock. And the reverse shock has actually been proposed to explain the optical counterpart, not the optical afterglow, but if there's a counterpart observation, it's found generally that the optical emission that's detected that is so coincident with the GRB, it doesn't scale with the GRB flux. So it kind of rules out the fact that they both have the same physical origin. So it has been modeled in terms of this reverse shock.
But from the opposite.
But from the opposite side, I don't think anyone thinks of that.
Any other questions? All right, let's thank our speakers. Also, there is a sign-in sheet going around. I appreciate if everybody could sign, on your way out. And we And students who are taking the Swift BAT XRT, please keep working on your draft and email me if you haven't already, so I know where you're at. Thank you.
Copy that? Or, actually, it should be on here.